what is the tension in the rope, and what's the reaction at A. So we want the pin reaction at A for equilibrium, and we want the tension. I'd say this is a more unique type of problem. Generally, we're doing this in the abstract and just trying to find the centroids. We have to start with that step, but now we have to go further and take it back to chapter 5 in order to find these unknowns. We're told that the steel has a density, which I'll call rho, of 7850 kilograms per meter cubed, and a constant thickness of 10 millimeters, or a uniform thickness of 10 millimeters. So the idea here is I won't go through the full body diagram yet, but this is why we're going to be doing this. So I'll redraw this later. We know we have a pin here. We know we have that tension here. So what we're looking for is we're going to have the weight of this steel plate somewhere, and because it's a weight, it's going to be pulling down. So what we don't know right now is what's the weight of the plate is one thing, and also where can we put that point force so that it's equivalent to this distributed value within the plate. So we don't know that weight, and we also need to know where to put it so that then we can do our sum of forces with that W, and we can do a sum of moments because we know where we're locating that force. So that Y bar, that X bar, and that W, those things are going to come from finding the centroid of the object. Once we have those, then we can look at the free body diagram because we know where to put the weight and what the weight is, and then we can solve for the other three unknowns, those reactions. So this is where we're going to get. I'll erase this for the moment though, and start by treating this just like the geometric shape like we saw in the previous example. So in this case, it goes from x equals 0 to x equals 4. It goes from y equals 0 to y equals 2. And it's bound on the top by y cubed equals 2x. So we want to find its centroid. And actually, if we find, we're going to have to find its area along the way. And we'll see how we can use that area to then find its weight. So our first choice here is, do we want to make vertical strips or horizontal strips? Again, that comes to what functions is it bound by. The right, the bottom, and the left are easy. It's this top one that's just a little bit more work. And this is really going to dictate or inform us of do we want to use a horizontal strip or a vertical strip. So what we want to think is it going to be less messy to isolate X or less messy to isolate Y? Right, in this case, it's almost already isolated, so I can rewrite this as x equals 1/2 y cubed. And we see y is now to the third power. Alternatively, if we isolated y, we would have had a cube root, which we would prefer not to have. So this tells us we are going to put everything in terms of y, and that says that we're going to use then horizontal strips rather than vertical strips. So I'll draw my one horizontal strip here so that we can then draw the other ones. So first thing is we need to find the area of each strip. If we're using the horizontal strips, then every strip is going to be infinitely thin or have an infinitely thin height of dy. And then we have to determine what its length is. So the area will be dy times the right x location minus the left x location. And then that will give us what this length is for any strip. Right, so for any of my horizontal strips, where is the right edge located in terms of a value? Right, it's at x equals 4. That's true for the top one, this one, and the bottom one. So everyone shares that same right edge of 4. But the left edge, that's going to change because up here, it's further from my axis, further from the origin. And then over here, it's closer to the origin. So that's going to be every one shares is located on this bounding curve. So every left is equal to this expressed in y. So this actually is xl, and my xr is 4. So the xl, I'm going to subtract 1/2 y cubed and multiply that by dy. What you want to make sure of when you're doing this is if dy is your differential, everything in here has to be either a constant or in terms of y. You should not have any x's here. That's why we're doing this replacement. Instead of calling it xr, I'm calling it 4 instead of xl. I'm referring to it in terms of y. You don't want to mix your x's and y's, or it's not going to work with that single integration. Any questions on making the dA, the area of any strip? I can find my area by then integrating the area of each individual strip. In this case, because I'm using horizontal strips, I want to see where is the bottom strip located in terms of y, which will be at y equals 0. And then I keep putting strips on top, on top, on top, and then the uppermost strip, that happens at y equals 2. So that's my upper bound is y equals 2 here. And I'll have 4 minus 1/2 y cubed times dy. I can integrate this, and because we chose the horizontal strips, I have just a polynomial expression for y, which makes this easier. Then I can take the antiderivative of my terms. The antiderivative of 4 is going to be 4 times y. And then I'll have minus 1/8 y to the 4th, evaluated from 0 to 2. All right, so I can integrate the first term, I can integrate the second term, I put them into this expression, and I can evaluate this at 2, and evaluate it at 4. So this will be 8 minus 2 to the 4th over 8, minus this evaluated at 0 is 0, this evaluated at 0 is 0. So I'm left with 8 minus 2 to the 4th over 8, 6 square meters as the area. We need to integrate y tilde dA over that total area. And to find y bar, we need y tilde dA divided by the entire area. What we didn't define yet the other day was what x tilde was and what y tilde was. Remember when we used the strip method, either vertical or horizontal, one of these values will just simply be either x tilde will be x or y tilde will be y. When we had the first example, we saw that with the vertical strips, x tilde was just x. When we have these horizontal strips, y tilde is just going to be y. So the centroid of every one of these strips is always just going to be y above the x-axis. So it's the reverse of what we saw before. Then we have to come up with what x tilde is. What's the distance between the y-axis and the centroid of each one of the strips that we have? It's really the same method we saw the other day, where it's going to be just the average distance or the average location of the left side and the right side, but as defined before. So the other day we said that the right side was always at x equals 4, and the left side of every one of these rectangles was at 1/2 y cubed. So in this case, we're taking the average of those two values, and that tells us the distance between the centroid and the y-axis, which is what we call x tilde. I have to distribute that, 2 plus 1/4 y cubed. So that's our x tilde. We have our y tilde. So now we can go to this step where we actually run the integration. We already know a from the other day on Wednesday was 6. So it's the numerator that we need to find next. And we're going to integrate this from y equals 0 to y equals 2. X tilde, this one will be the harder one, 2 plus 1/4 y cubed, multiplied by our dA here. We have to FOIL this out in order to, or we can FOIL this out in order to do our integration. We have the y cubed term and we have a constant term here. This will simplify though once we FOIL it because they both have a constant and a cubed term. So I actually skipped this step where I FOILed it out, but we take the antiderivative, and for this we're going to get, put this together, 8y minus y to the 7th over 56, evaluated from y equals 0 to y equals 2. This value is 13.7. And this will be in meters to the 3rd power. We have the numerator now. We knew the denominator was 6. So for x bar, we have 13.7 over 6. We find that x bar is 2.29 meters. Right, so for y bar, we do the same thing, but with y tilde instead of x tilde times dA. This one will be simpler to do because we know y tilde is just y, and we're going to multiply that by dA. We'll get 4y minus 1/2 y to the 4th dy. So we don't have to worry about FOILing it here. I can take the antiderivative. I'll have 2y squared minus 1/10 y to the 5th power, evaluated from 0 to 2. And I'll get 4.8. I divide that numerator then by a, so I'll do 4.8 divided by 6, and that gives me my value for y bar. So y bar is going to be located at 0.8. I have my area, I now have my x bar, I have my y bar, so I know where the centroid is located, and I know what the area of my shape is, which I need in the next step when I go back to looking at or create a free body diagram and then analyze my free body diagram. Questions on the calculus steps in this one? All right, the reason I went through all this, now I'll draw my free body diagram. So I'm out of the kind of just abstract math portion of it and go back to what are the forces acting on my steel plate. So on the plate, it's pinned at A. It has this tension at B. So I'll put that tension in. And I have the pin at A. So just like pins we saw before, I have that AX and that AY. Now what I can do is I have to put in the other force that acts on the plate, which is the force of gravity. And the force of gravity, because it's homogeneous, is going to act at its center of mass, which because it's homogeneous, is located at the centroid of the shape. So the centroid is what I just found. Since in my math step, I said that the origin was located at A, then these numbers are telling me how far from A in the x direction and the y direction is this point located. So the x bar is 2.29, so I need to go 2.29 meters to the right of A to get to that centroid. And from the x-axis as defined here, I have to go up by 0.8 meters. And what that tells me is that's where I can locate the weight of the plate. However, I don't know right at this moment what that weight is, but I do know where it is. How can I find what the weight of my plate is? Right, since I know basically the surface area of the plate, and I'm told it's a uniform thickness, I can find the volume of the plate. And once I know the volume of the plate, I can multiply it by the density that we were provided, since that's kilograms per cubic meter, and then I'll know the mass of the plate then, and then I can easily find the weight from there. So the volume is its surface area times its thickness. Once I know the volume, then I can get the mass. Actually, I'll skip that step too. The weight is going to be the mass times gravity. The mass is going to be the density times my volume. And the volume is A times T. So putting it all together, I get my density times my area times my thickness. Again, that's my volume. That's my mass. And then I'm going to multiply that by gravity. And in this case, that's 9.8 meters per second squared. So if I multiply all of that together, I get 4,620 newtons as the weight of my plate. So I know where it acts, and I know the value of the weight at that point. My free body diagram now has T, AX, and AY that I don't know, and then one applied force or one acting force, the weight of the plate acting through the centroid of the object. Now it just looks like something we have from chapter 5, and we can find those three equations, equilibrium equations, to get ultimately what we needed, the tension in the rope and the reactions at the pin at A. The only thing in the x direction is AX. That will be 0. If I take the sum of moments around A, I will have the tension that's located 4 meters perpendicular from A, and that's causing a positive moment, minus the weight, and I know how far that is from A because I know where the centroid of my shape is. And those are the only two things that cause a moment around point A. Therefore, the tension in the rope is going to be 2,650 newtons. And when I sum forces in the y, I get my T, I get my AY, minus the weight. I know my T, so I can find AY is 1980 newtons.